Hi everyone, this is Professor Fernandez, and in this video we were talking about Module 3 in Lesson 15. We're still working on vector fields. In this module we're going to talk about the curl and divergence of vector fields. So let me run through this definition and give you some more insight and information about what those are. I'm going to suppose for the moment that F is a vector field with three components, meaning that we're thinking of this vector field as being plotted in three-dimensional space. And then down here, we will go to the case when F is just a two-dimensional vector field. I'm also going to assume it's differentiable because the curl and the divergence are defined in terms of derivatives of the components of the vector field. So the curl of F, I'll just show you in a moment how it's defined, but let me talk about the notation. First of all, this is a notation for the curl, and you'll notice that it's a cross product of the del operator. This should be familiar. Remember this operator from the gradient. And the vector field F itself. So if you think back to what the cross product generates of two vectors, right? The cross product of two vectors generates another vector. So in this similar sense, the cross product of a vector field will generate another vector field. And then also think back to what the cross product's components are. They're somewhat complicated differences of products of each of the components of the two vectors. A similar thing is happening here. So we have differences of, but in this case, not products, combinations of the first components. The components of the del operator are derivatives. And then the other components of the second term here, which is the vector field, its components are the functions f, g, h. So I'm trying very hard to convince you that, the curl in a way is nothing special because it really is just another cross product of two very different things in what we were cross-producting before, which is just two vectors. In this case, the del operator, which has a bunch of derivatives in it, and derivative operators, and the vector field f, which has functions in it. That being said, here is the definition of the curl of a vector field f. Again, it's not very intuitive what this means, where it comes from, or what its importance is. We'll talk a little bit about that in this video, but we'll see much more information about that in the next lesson. And then I'll mention one more time that I will show you how to come to this definition using the same processes we used when we were taking cross products of two vectors, specifically the determinant version of the cross product. Okay, so then let me talk about the second thing in this definition here. This is the divergence of a vector field f. So following the same idea, this was the cross product of the del operator with the vector field f. This one is the dot product of the del operator with the vector field f. You might remember that cross products produce vectors, dot products produce numbers. That was in the earlier part of the course where we were taking cross products and dot products of vectors. We're now taking cross products and dot products of vector fields. So as we just talked about, the curl of the vector field produces another vector field. The dot product of the vector field f produces a function. So notice here that there are no vector symbols here because we're not getting a vector, we're getting a function. And then surely if you give me a point, I could evaluate each one of these three terms and that would yield a number, which is what we would normally get out of a dot product if we were dot producting two vectors. So how is the divergence of a vector field f defined? You literally take its components and you differentiate them with respect to x, y, and z in that order. So partial of f with respect to x plus partial of g with respect to y plus partial of h with respect to z. And that is the curl. Okay, so everything that I've just said assumed that the vector field was three-dimensional. So what if I now assume that the vector field is two-dimensional? We've been working a lot with 2D vector fields in this lesson because they are easier to draw and picture. So if I make the same assumptions that it's differentiable, then the curl and divergence are defined as follows. The curl is defined as just the last part here of the three-dimensional curl. So it's just that component, and it technically we don't need this, but I've put it in to be consistent because this should yield a vector field, so there should be some vectors on the right hand side. So in other words, we just pick out this component, which is in the z component. So it is this quantity times k hat, which points in the positive z direction. So that's the two-dimensional curl. So the divergence we define as similar to what we just did. So we pick out the parts that involve only f and g. There is no h here in the vector field, so any part that involves h for the divergence we throw away. So the divergence here is just the partial with respect to f of x plus the partial with respect to g of y. Great, so let me then mention what I had alluded to earlier. The curl of f can be calculated as a determinant of this matrix. What am I doing here? This might seem a little strange, but we're taking the del operator, pretending that it's a vector, and we're putting its components here, just like we would if we were calculating the cross product of, say, A cross B. We would take the components of A, and we would put it in this first row, A1, A2, A3. And then we would take the components of the vector here, which are f, g, h, and we're putting it down here in the last row. Just like over here in the cross product, we would put the components of b down here. And then if you calculate out, just like we did over here with our 3 2x2 determinants and alternating the signs and all of that, you get this expression up here. The last thing I'll mention there is that you'll have to interpret, for example, if this is my submatrix and I want to take the determinant of this submatrix, then you'll have to interpret products as differentiation. So for example, the determinant, the product, quote unquote, of these two would be partial g, partial x, whereas the product, quote unquote, of these two would be partial f, partial y. Partial g, partial x minus partial f, partial y, you see that that's one of the terms in the curl. Okay, the notation, second note, the notation for both curl and divergence, as we mentioned, can be understood by using the usual rules of dots and cross products and the del operator. So the del operator is to be thought of as a vector operator in the same way as we thought of d by dx as the differential operator. So, back from calculus, you might see derivative rules written in this form, for example, and we were thinking of d by dx as a differential operator. It takes a function, it produces another function. I want you to think of the del operator in the same way. So this is just a vector of derivatives, and it takes a vector field like this one and produces other vector fields, except now we have these somewhat richer ways to produce other mathematical objects from the del operator. We can take cross products, we can take dot products, for example, or we can just take gradients of a scalar field. Great, so those are the two big comments that I wanted to make. So you might be wondering, where did curl and divergence come from? I've hopefully convinced you that mathematically this is a somewhat sensible thing to do. You have a del operator, you have a vector field f. Why not look at the cross product and the dot product? Those are two operations we've been working with a lot. But there must be some reason for this. There must be some usefulness for these concepts. So indeed, they are useful, and they tell us different things about the vector field. And we'll start scratching that surface here. We're not going to get fully into it. We'll do that in the next lesson, but I did want to just set that up. So this example says calculate the curl and the divergence of the vector field in number 3, in example 15.3, and then the one in 15.4. So the first one in example 15.3 was 0 and x. And the second one in this other example ended up being the gradient that we calculated. If you go back and look at the video from module 2, was 2x and 2y. Great. So at this point, what I'm going to do is calculate the curl and divergence of both these vector fields to illustrate for you how you do this calculation. We are going to get fairly simple answers, and the calculation is going to be fairly simple. In a regular, setting, you might have to do a little bit more work. You'll see that in the practice problems. But again, I just want to plant the seed for a discussion in the next lesson of what these curl and divergence objects measure. Okay, so let's talk about first the divergence of this vector field. So let's identify f here and g, and the divergence of the vector field is partial f partial x. plus partial g partial y. So f does not depend, it's a number, so I just get 0. G does not depend on y, so I also get 0. So I get that my divergence of f is 0. Okay? Surely anytime you get 0 in math for a calculation, there might be something interesting going on that you might want to investigate. So this is a little clue. Second one is the curl. So this is a two-dimensional vector field. So I'm going to scroll up and remind you what the curl is for that two-dimensional case. Here it is. So gx minus fy in the z direction. So gx minus fy in the z direction. Okay, g does depend on x, and its partial with respect to x is 1. F here is a number, so its partial is 0. So I get just k hats. So in other words, the curl is not 0. It's equal to 1, effectively, in the k hat direction, which is always the direction the curl points in for a two-dimensional vector field. But the divergence is 0. So I'm going to come back to what this means in a little bit, but I first want to calculate the curl and divergence for this other vector field, and then we'll start contrasting and comparing. So divergence here of the vector field f, again fx plus gy, and here is my f. It does depend on x. Fx here is, fx there is 2. And then gy, well, this is 2y. Partial with respect to y here is also 2. So I get 4. So this vector field does not have a 0 divergence. This vector field does have a non-zero divergence, a positive one specifically. And then I'm going to go back and find the curl of the vector field f. So gx minus fy in the z direction. And I go back, and g here only depends on y. So gx is 0. F only depends on x. So fy is 0. So I get 0 for my curl. Curl of f equals 0. And this is the 0 vector, so technically I'll write that in there. And I have now calculated the curl and the divergence for these two vector fields. And let's think a little bit about what is going on and what they might tell us. I won't scroll up because then we'll lose this, but I'll just try to draw it here as best I can. Remember that this vector field at the very start of Module 2, when we talked about graphing this vector field was a shear vector field. So it looked a little bit like this. So if we graphed it, and I'll do this for you with technology in a moment, we had these arrows that went up if x was positive, and then the arrows got bigger as you went away from the y-axis. And then on the left-hand side, the arrows were small. Similar behavior, they got longer as you went away from the y-axis. So this was just shear field. So what we're learning here is that the divergence of this shear field is 0, but the curl is non-zero. And remember, we had talked in that module that, if I imagine putting a little bar here, because of, as you see, the way the vector field is arranged, this bar would tend to rotate. This part, the right-hand part, would go up, the left-hand part would go down. And, we have a 0 divergence and a non-zero curl. So perhaps the curl has something to do with rotation. So that's the first thing we might learn from, guess from this very simple example. The vector field over here, on the other hand, this is just going straight out from the origin in a radial direction. So, and these arrows get longer the further away from the origin you get. So this was the plots, rough, very rough plots of this vector field, and I'll show you this with technology again. I described this in the Module 2 video as kind of like an explosion from the origin. So if you imagine a particle, somewhere over here, it just gets thrust out away from the origin. This vector field has 0 curl. So if we're thinking, as we were perhaps starting to think here about curl measuring rotation, that would make sense. There doesn't seem to be any rotation happening here. it does have a non-zero divergence. So what could divergence possibly mean? Well, the main difference between these two vector fields here, if I had to describe it qualitatively, is that there's some rotation going on here, but there's doesn't seem to be movement away from the origin. You can again imagine this little bar here being rotated this way, and it just continues to be rotated. It's feasible that it might just be continue to be rotated and go back to where it was. It wouldn't necessarily move away from anywhere. Whereas, any particle you put here is just going to be blasted out away from the origin, but not in a rotational manner. It's not going to curve away from the origin this way. So we might associate then, we might think of divergence as measuring something like the tendency to move away from a point, or in this case, perhaps the origin. So I'm going to show you these things again in terms of technology. So over here is the vector field that we talked about first, which is the x 0, comma x. So that's down here that I've plotted it. And you can see again, this is the on the negative x axis. The vector field moves you down, and the further away you get from the origin, it does that with more force, if you will. Positive x-axis, it moves you up, and the further away you get from the origin, it does that with more force, if you will. So again, if we look at, and notice I did it right there, if I put a point here, what the program is doing is that it's plotting the flow curves. Remember, the flow curves are the curves whose tangent vectors are the vector fields. So, anywhere I go on the right axis, x positive axis, my flow curves take me up, and here my flow curves take me down. But again, as you can see through this picture, there's movement this way, there's movement that way. So if I put a horizontal bar here, it would get rotated up that way and rotated down this way. Let me show you then the vector field that is the 2x and 2y one. So this was the explosion, so to speak, vector field, right? And if I put any point there, I'm going to show you the flow curve. I just tap there, and it just sends you off away from the origin in a straight line. I'll see in a line. All lines are straight. In a line, and so you have no rotation. So again, we have some sense that perhaps divergence measures this type of property of vector fields, being blasted away without rotation, and that perhaps curl measures a little bit of this type of property of vector fields, the presence of rotation. Certainly you can have vector fields in which you have both rotation and some measure of being blasted away. And then also we might think about the fact that, this is a positive number that we got for the divergence. What might it mean to get a negative number? Well, we can kind of glean that from here. What if this was negative 2x and negative 2y? So that these vectors from the vector field literally pointed inward, the opposite direction. So this wouldn't be as much an explosion as it would be something like a black hole. Everything is getting sucked into the origin. Well, you can see if we made this negative 2x and this negative 2y, it would be a negative here, and we get negative 4. Aha! So maybe a positive divergence tells us a little bit about the explosion nature of a vector field being blasted away from a point. And maybe a negative divergence tells us about, a black hole type nature of a vector field being sucked into a point. You will later perhaps hear the words sources and sinks. So when you have a negative divergence, you think of a sink, like when you run water down your drain, it sinks into the center of the drain. And a source being like the actual explosion that we've been talking about, things move away from the point. Similar thing with over here, we got a positive curl. And, if you notice the way the vector field is rotating this little bar that I've been drawing, it rotates it, the bar starts off this way, and then it rotates it that way. So counterclockwise, which we associate with positive angle measures. So perhaps a positive curl rotates in one direction, perhaps a negative curl rotates in the other direction. So, this is as much as I want to say at this point about these concepts. Again, we will talk much more about them in the next lesson, but I've hopefully planted the seed that perhaps curl measures something about the rotation of the vector field. There are lots of subtleties there that we'll briefly mention in the next video, But, and also perhaps divergence measures something about the source or sink nature of a vector field. Great, so that's it for this video. I'll see you in the